Hi friends, now we are going to see last part of MATLAB Onramp course on reinforcement learning RL. Let us start. In this video we will cover train agents topic and then conclude these course. In this slide we have list of sub-modules that we are cover in this video. Okay. Training an agent. A schematic of the whole RL training process, with a box representing the agent interacting with a box containing a Simulink model representing the environment. The agent's actions affect the environment. The environment provides observations to the agent. Within the agent are boxes representing the actor and critic containing neural network icons. The agent also contains a box with a gear icon, representing the training algorithm. The environment provides rewards to the training algorithm within the agent, which, in turn, updates the actor and critic networks. During training, the agent receives rewards from the environment, and these rewards are used to update the policy. The training algorithm specifies how the parameters of the actor and critic are modified in response to the rewards. Once you have the variables that define an agent and an environment, you can pass these to the train function. By default, training progress is displayed in a new window. The plot shows the reward earned in each episode. Generally, you want to see the reward increasing as training progresses. However, randomness in the agent's choice of action and its interaction with the environment will result in variation in the reward received in a single episode. Progress is therefore judged by averaging over a number of episodes. The red line shows the reward averaged over a moving window of episodes. Training progress is displayed in a new window. The plot shows the reward earned in each episode. Generally, you want to see the reward increasing as training progresses. However, randomness in the agent's choice of action and its interaction with the environment will result in variation in the reward received in a single episode. Progress is therefore judged by averaging over a number of episodes. The red line shows the reward averaged over a moving window of episodes. If the agent includes a critic, by default the progress plot will show the critic's prediction for the reward value for each episode. Ideally, the critic's prediction should start to match the actual reward as training progresses. This indicates that the critic is learning to accurately evaluate the value of being in a particular state. If the agent includes a critic, by default the progress plot will show the critic's prediction for the reward value for each episode. Ideally, the critic's prediction should start to match the actual reward as training progresses. This indicates that the critic is learning to accurately evaluate the value of being in a particular state. Training stops when a maximum number of episodes has been reached or when a success criterion has been achieved, such as the average reward reaching a given threshold value. You can also stop training by clicking the Stop Training button. Unlike many MATLAB functions, the train function does not return the modified agent as an output. Instead, it updates the agent directly as training progresses. The output from train is a structure containing information about the training progress, similar to what is shown in the progress plot. Training options. When should training stop? What success criterion do you want to use to judge training progress? These are the options you will typically want to set to control how training progresses. Task 1. You can use the RL Training Options function to create a variable containing the settings for options on controlling training. With no inputs, RL Training Options returns the default options. Opts is equal to RL training options. Task. Use the RL training options function to create a variable called opts that contains the default training options. You may want to leave off the semicolon to see the results. Syntax. Opts is equal to RL training options. And output shown in output panel. Task 2. You can specify the value of training options by calling RL training options with any number of input pairs. Opts is equal to RL training options, option name, value. Because each dice game is typically short, it makes sense to lower the maximum length of a single episode and raise the maximum number of episodes. Task. Use the RL training options function to create a variable called dice opts that sets the max steps per episode option to 20 and the max episodes option to 2000. Syntax is dice opts is equal to RL training options, max episodes, 2000 max steps per episode, 20. And output shown in the output panel. Task 3. Once you have training options variable, you can use variable property syntax to modify an option. Opts. Option name is equal to option value. With many episodes with large random variation, it makes sense to increase the number of episodes from which to calculate the average. Task. Modify the score averaging window length property of dice opts to have the value 100. Syntax is dice opts. Score averaging window length is equal to 100. Output shown in output panel. Task 4. By default, training stops if the episodes take the maximum number of steps, 500, on average. The length of an episode is a good success criterion when you want an agent to keep performing a task without failure, such as a drone hovering or a rover avoiding obstacles. For the dice game, however, shorter episodes are better, so it makes more sense to use the reward as the stopping criterion. Task. Modify the stop training criteria property of dice opts to have the value average reward and the stop training value property to have a value of -3. Syntax is dice opts.stop training criteria is equal to average reward. Dice opts.stop training value is equal to -3. Output shown in output panel. Further practice. The command that is commented out shows how you can pass the training options variable as an extra argument to the train function. You can uncomment this line to train the agent. Note, though, that this can take several minutes. You can always use the stop training button to end training early. Note that the untrained agent might achieve a high episode score by luck. If this occurs early in the training, it can result in the training being stopped immediately because the average reward threshold was reached. In this case, you can run the training again. You can add the commands. Trained critic is equal to get critic, agent. Visualize queue, trained critic. To visualize the queue table of the trained agent, you can also use the command n when is equal to play dice, agent, SLENV. To simulate playing the game with the trained agent. After following above syntax, then one window will open as shown here. Then after training with 130 and more episodes, we will output as shown in the output panel. Okay. How to define your environment including the rewards that your agent will receive, create your agent, and pass the environment and the agent to the train function. You've also set training options to control aspects of the training process, such as the stopping criteria and the maximum number of episodes to run. Agents also have a number of options, often referred to hyperparameter, that control the details of how agent explores and learns. Some of these you'll want to set before training. Others you'll want to experiment with to help the agent learn better. But what do all the options do? How do they affect training? What is training anyway? There are different types of agents, each with their own set of options. Yeah, it's a lot, but don't worry about trying to remember all the details. That's what documentation is for. Instead, understanding the basic idea of how training works can help you understand the various options in broad terms. You can learn the details as you need them. So what does happen when you train an agent? Recall that at the heart of an agent are the neural networks that represent actors and critics. These networks contain many parameters, the weights and biases. It's these parameters that determine how the networks turn observations into actions or values. And it's these parameters that update during training. When you were first playing the game, you didn't really know the value of having your warrior on the bridge at this point. But after playing out the game, you have a better idea of the value because of the feedback you got from the game. So now you should update the parameters of your critic network to give that better value estimate when it sees that situation again. Similarly, with the critic just guessing its values, you didn't know whether it would be better to move your warrior onto the bridge or play your adventure card, so your actor was choosing actions with no particularly good reason. But now that your critic is better at estimating values, you can update your actor to be more likely to choose the highest value action. If you know about other machine learning applications, this might sound familiar. It's a lot like supervised learning. That's when you want to train your neural network to produce known correct outputs for given inputs. So updating the actor and critic parameters is done using standard machine learning algorithms with the correct outputs determined by what you learned while playing the game. Typically, the algorithm is some form of gradient descent. You'll see a bit more on how gradient descent works later in this lesson. Naturally, the gradient descent algorithm also has options you can tweak. You can set the algorithm options for both the actor and the critic to control how they learn, but RL isn't just supervised learning in disguise. Firstly, do you really know the value of having your warrior on the bridge? You can assign it a value based on how things went after that one time you tried it, but you are still learning, so how accurate do you think your value will be? If you had the world champion sitting next to you, then you could do supervised learning. Just ask them for their estimate of the value and learn to replicate what they say. But in RL, there's no mentor, just your own experience. So when you update your agent, you are doing supervised learning with correct values of unknown correctness. And if that wasn't difficult enough, remember that you are playing and learning at the same time. Moving your warrior onto the bridge seems to have been a successful move, so should you use that knowledge to change your strategy right away? It seems crazy to keep using a bad strategy when you know a better one. But do you know a better one? You can't evaluate how good a strategy is unless you let it play out. So how long should you play with your current strategy before you switch to one that you think is better? Different agents handle this in different ways. And of course, they have options to control the details, but ultimately, these are all just variations on how the agent explores the environment. uses those experiences to evaluate states and actions and updates the network parameters according to those values. In the rest of this lesson you'll learn a bit more about the agent options and then gradient descent and the actor and critic options. Functions for specifying options. A schematic of the whole RL training process, with a box representing the agent interacting with a box containing a Simulink model representing the environment. The agent's actions affect the environment. The environment provides observations to the agent. Within the agent are boxes representing the actor and critic containing neural network icons. The agent also contains a box with a gear icon representing the training algorithm. The environment provides rewards to the training algorithm within the agent, which, in turn, updates the actor and critic networks. The agent is labeled with a MATLAB object icon and a function RL*agent. There is another object icon with a function RL*agent options. You can create different kinds of agents with the various RL*agent functions. Each of these functions has a corresponding RL*agent options function you can use to control how your agent learns. For all agents, you can set the discount factor and the sample time. The discount factor determines how the rewards at the individual time steps are weighted. This allows you to make the agent more short or long-sighted. The sample time determines how frequently the agent interacts with the environment. The Simulink model simulates the dynamics of the environment through time, choosing the time steps at which to update the internal state of the environment. This is independent of the agent's sample time. Regardless of the internal dynamics of the environment, the agent receives observations and takes an action once every increment of sample time. Each agent also has specific options. Generally speaking, these control how the agent explores the space of possible states and actions by taking actions either according to the policy or at random. Stores and uses previous experiences to learn. Updates its policy, such as how frequently an actor-critic agent should update the critic. Check the documentation for the details on the options specific to each type of agent. You can also specify the options that control how your agent's actors and critics are updated during training. In particular, you will often need to adjust the learning rate, the learn rate option, which determines how aggressively the parameters are changed in response to new experience. Training typically uses some form of gradient descent to adjust the parameters. How much the parameters are changed is therefore related to both the learning rate and the size of the gradient. You can limit the size of any update by using the gradient threshold option to set an upper bound on the size of the gradient. The gradient descent algorithm is ultimately an optimization algorithm, in this case minimizing the error in the actor or critic's desired output. Hence, the options are stored in the actor optimizer options and critic optimizer options properties of the agent options. You can use the RL optimizer options function to create variables to hold the settings for your actors and critics. Use these variables as the value of the agent's actor optimizer options and critic optimizer options properties. Task 1. You can specify the options for an actor or critic by calling the RL optimizer options function with any number of input pairs. Opts is equal to RL optimizer options. Option name, option value. If training does not seem to be converging to a reasonable policy, you can try updating parameters less aggressively by lowering the learning rate or limiting the size of the gradient. Task. Use the RL optimize options function to create a variable called critic opts that sets the learn rate option to 0.001 and the gradient threshold option to 1. Syntax is: critic ops is equal to RL optimize options, learn rate 0.001, gradient threshold 1. And output shown in output panel. Weighting future rewards. The value given by a critic is the total accumulated reward from the current time through the rest of the episode. However, an action's influence over the future state of the environment typically decreases through time. For example, applying a force to a robot will change its state immediately. That state will then affect subsequent states in the short term. That short-term influence will, in turn, contribute to the long-term success or failure of the agent. However, future actions will also affect the long-term behavior and more directly than current actions. Hence, future rewards are typically discounted. The further into the future, the less the reward is counted toward the value of the current state. The value given by a critic is therefore the total accumulated discounted reward. Current value is equal to immediate reward plus discount factor asterisk future value. The discount factor, usually denoted by gamma, is an option you can set. A discount factor of 1 means that all future rewards are equally weighted. A factor of 0 means only the immediate reward is considered. A value between 0 and 1 means future rewards are discounted exponentially with time. In MATLAB, agents have a default discount factor of 0.99. You can specify the options for an agent by calling the RL asterisk agent options function corresponding to your choice of agent. For example, to specify the options for a DQN agent, use RL DQN agent options. As with all options functions, you can specify any number of input pairs. Opts is equal to RL DQN agent options. Option name, option value. For the dice game, the goal is to reach the target in as few steps as possible. This means the agent should consider the reward for the entire episode. To make an agent as far-sighted as possible, set the reward discount factor to its maximum value, 1. Task. Use the RLDQN agent options function to create a variable called agOpts that sets the discount factor option to 1. Syntax is: agOpts is equal to RLDQN agent options, discount factor 1. Output shown in output panel. OK. Task 3. You can use dot notation to modify the properties of an existing options variable. Opts is equal to RL optimizer options. Opts dot property is equal to value. Task. Use dot notation to modify the critic optimizer options property of agOpts to contain the options stored in critic opts. Syntax is: agOpts.critic optimizer options is equal to critic opts. Output is shown as in the output panel. Random exploration. During training, a Q-learning agent follows an epsilon greedy policy. Generate a random number between 0 and 1. If it is greater than epsilon, take the action with the greatest value. If not, choose an action randomly. The parameter epsilon is the proportion of times the agent will take a random action. This determines how much the agent explores. If epsilon is equal to 1, the agent always explores randomly. If epsilon is equal to 0, the agent always follows the highest value policy and does not explore at all. Typically, you want to explore more at the start of training and less once the agent has started to build an estimate of the Q value function. A common approach is to start with a high value of epsilon, then decrease it after each training episode, usually with some minimum threshold to ensure that the agent continues to explore, even after many training episodes. The initial value of epsilon, the rate at which it decreases, and the minimum value are all parameters that control how a Q-learning agent trains. Task 4. Some options, like the discount factor, are just values. Others are variables with multiple properties. You can use variable.property syntax to access and modify the properties of these options. Opts.optionName.property is equal to value. Task. Modify the epsilon decay property of the epsilon greedy exploration option of AG opts to have the value 0.001. Syntax is agops. Epsilon greedy exploration dot epsilon decay is equal to 0.001. Output is shown as in the output panel. Task 5. All of the RL asterisk agent functions except an options variable created the corresponding RL asterisk agent options function. Opts is equal to RL DQN agent options. Agent is equal to RL DQN agent opts. Task. Use the RLDQN agent function to create an agent called agent with the options stored in AG opts. Recall that the observation and action information are stored in the variables obs_info and act_info, respectively. Syntax is agent is equal to RLDQN agent, obs_info, act_info, AG opts. Output is shown as in the output panel. Further practice. The commands that are commented out train the agent with a certain set of training options. You can uncomment these lines to train the agent. Note, though, that this can take several minutes. You can also download the course files from the help menu in the top right corner. Alternatively, you can use the command load trained agent to load a previously trained agent from file. Either way, you can use the command visualize Q agent to visualize the Q table of the trained agent. You can also use the command n when is equal to play dice agent SLENV to simulate playing the game with the trained agent. A new window will open after running the given syntax as above. OK. After 128 episodes, the output is shown as in the output panel. Training the warehouse robot agent. So far, you've defined the environment for the warehouse robot with a reward function designed to guide the robot to the goal, and created a DDPG agent with default actor and critic networks. However, training with default options does not produce good results. It is very rare that training works well with no adjustment of options. In this activity, you'll set some of the options that allow the robot agent to train effectively. Task 1. When the warehouse robot is trained with the default options, the episode rewards seem to jump around randomly. The robot is not learning anything useful. This can indicate that the training algorithm is being too aggressive in how it updates the agent. Common ways to address this is to lower the learning rate or put a cap on the size of the gradient. Task. Use the RL optimize options function to create a variable called learn opts that sets the learn rate option to 5e5 and the gradient threshold option to 10. Syntax is learn ops is equal to RL optimize options, learn rate, 5E5, gradient threshold 10. Output is shown as in the output panel. Task 2. Agents observe the state of the environment and take actions at a fixed rate. For the robot navigating through a warehouse, there is a hardware limit on how quickly the robot can or needs to make measurements and actuate the motors. The frequency of the agent's observations and actions is set with the sample time option. Note that this option should be set before training the agent at all. The other options set in this activity would be adjusted in response to training performance. The actor and critic networks are updated using stochastic gradient descent, meaning that the gradient, the direction in which to update the network weights, is estimated from a random sample of experiences. Increasing the sample size can provide a more accurate estimate. You can set the total number of episode steps to store with the experience buffer length option. The number of random samples to take from the buffer to estimate the gradient is the mini batch size option. Task. Use the RLDDPG agent options function to create a variable called agent opts that sets the sample time to 0.25, the experience buffer length to 1E6, 1 million, and the mini batch size to 128. Syntax is: agent ops is equal to RLDDPG agent options, sample time 0.25, experience buffer length 1E6, mini batch size 128. Output is shown as in the output panel. Task 3. Actors and critics can share the same options or each have different options. Task. Use dot notation to modify the actor optimizer options property of agent ops to contain the options stored in learn ops. Similarly, also modify the critic optimizer options property to contain learn ops. Syntax is: agent ops dot actor optimizer options is equal to learn ops. Agent ops dot critic optimizer options is equal to learn ops. Output is shown as in the output panel. Task 4. Use the RLDDPG agent function to create a DDPG agent called agent with the options stored in ops. Recall that the observation and action information are stored in the variables obs_info and act_info, respectively. Syntax is: agent is equal to RLDDPG agent, obs_info, act_info, agent ops. Output is shown as in the output panel. Further practice. The commands that are commented out train the agent with a certain set of training options. This agent takes several hours to train. You can use the sim function to see how the robot behaves with random weights, or you can load an agent from primedagents.mat. This file contains an agent called partially trained that was trained for 2000 episodes and an agent called fully trained that was trained until it achieved the average reward goal given in the training options. If you want to experiment with this example yourself, you can download the course files from the help menu in the top right corner. After following above syntax, we will get a window as shown in figure. Then after some episodes, output is shown as in the output panel. Strategies for improving training. Reinforcement learning is challenging. Successful training often requires many iterations, adjusting options and hyperparameters. What can you try when your agent doesn't seem to be learning? The answer for this question given here. Okay. Up to now we see the train agents topic and subtopics in that. Now we are going to start conclusion for MATLAB Onramp course on reinforcement learning. Okay. Summary of functions for the RL workflow. The diagram below shows the interaction of the functions you will typically use to create and train a reinforcement learning agent. MATLAB object icons with the functions that create them, organized into groups. Group 1 is define environment, containing RL * spec, twice, once for the observations and once for the actions, and RL Simulink environment. Group 2 is define agent, containing RL optimizer options, RL * agent options, and RL * agent. Group 3 is train agent, containing RL training options and train. Group 4 is verify agent behavior, containing RL simulation options and sim. Arrows connect the various functions. Reinforcement Learning Designer. Rather than do everything programmatically, you can also build and train agents in the Reinforcement Learning Designer, which you can start from the Apps tab in the MATLAB toolstrip. You can import agent and environment variables from the MATLAB workspace. You can create new agents directly in the app. The compatible algorithm menu lists only the types of agents that are valid for your environment. You can create new agents directly in the app. The compatible algorithm menu lists only the types of agents that are valid for your environment. Once you have an agent, you can set the options, including those for the actor and critic. Once you are satisfied with your settings for the agent, click Train. You can set options and start training. You can set options and start training. Once training is complete, you can simulate with the trained agent to verify its behavior. You can see a summary of the simulation results or look in detail at individual simulations to see the observations, actions, and rewards. Yeah friends, we completed the MATLAB Onramp course on reinforcement learning. Overall it takes 6 videos complete. Then these are further related topics given here, and thank you friends. We will meet in the MATLAB Onramp course on Simulink. Bye.